Thank you so much for this opportunity to present my work. Most of it is done at the University of Michigan, where I'm an assistant research scientist. So my name is Nishtha. I've been at U of M now for about 4.5 years. And I did my PhD in India, where I worked on coronal mass ejections, which is what I'll talk about, but mostly I did analytical work there, and now I'm doing numerical modeling. So I will talk, okay. I'll just check, people online can hear me? It's recorded.
Absolutely perfectly.
Thank you, okay, great. All right, then I'll start. So what I'll talk about today is numerical modeling of phenomena that is related with the sun, so solar wind and coronal mass ejections, but these are phenomena that impact space weather. So I believe it's slightly different from the research activities in this department or here, but what I'm hoping we'll get out of this is how these techniques can be applied to stellar phenomena, hopefully. Okay, so these are the main takeaways that should come out of this presentation. Firstly, what and why is space weather prediction really important? Then, because space weather has been an important topic of research for a while now, there have been many observational missions that have been commissioned. And so how do we connect those observations with numerical modeling? And with observations and with modeling come uncertainty, limitations in observations, and how does that data is used for improving our space weather modeling. And of course, if it can be used in other fields. Okay, so we start with what is space weather and why are we so interested in it? All right, so space weather in general is defined as any variation in the near Earth conditions, which is informed or which is because of activities that happened on the sun. Those activities or those phenomena can be the solar wind, which is a continuous stream of charged particles that flows out from the sun. It can be coronal mass ejections, which are these huge, large-scale blobs of plasma and magnetic field that are launched out of the solar corona. Then there are solar flares, which are sudden bursts of electromagnetic radiation. And these phenomena also energize and accelerate particles, which are known as SEPs, or solar energetic particles. So in these videos, actually, you can see a solar flare that's erupting. So it's like a huge flash of light that comes out. That is a typical observation of a solar coronal mass ejection, where the disk of the sun is this white ring, and a large space around it is occulted because the solar corona, or the atmosphere of the sun, is dim but extremely hot. So to visualize that, and it has stopped. Yeah, okay. So to visualize that, we occult the part of the solar corona so that we can see energetic blobs of plasma that are coming out, and I'm not sure why this is playing. This is not playing. But this is what a CME looks like, and there's a relative representation of how small the Earth is in comparison to the sun. Okay. So couple of more details about what CMEs and solar wind is, because that's mostly what I will be talking about. So the solar wind, again, is like a continuous flow of charged particles and magnetic field from the atmosphere of the sun out into the heliosphere. The solar wind speeds can range between 250 to 750 kilometers per second, as observed at Earth, and the density is between 3 to 10 particles per cc. This is an iconic representation of the solar wind. Speed and its latitudinal dependence, which is taken from Ulysses. So you see that solar wind is pretty slow when it comes out from the equatorial regions of the sun, which is yeah.
What is CC?
CC is cubic centimeters. Yeah, sure. Right, so which is dominated by closed magnetic field lines, and regions that have fast solar wind associated with it come from the polar regions or higher latitudes, where the magnetic field lines are more open. That's okay. And then what are coronal mass ejections? As the name suggests, it is a massive ejection from the solar corona. When I say massive, they are about 10⁻15 grams. Typically, the speeds can range from slow CMEs, which is a few hundred kilometers per second, and the fastest CMEs observed are over 2,000 kilometers per second, but they are rare. On an average, when the solar activity is really high, there are about 4 to 5 CMEs in a day. When it's pretty low, there's maybe one CME or a coronal mass ejection in a day. The magnetic field of a CME can be thought of as a slinky. So if you think about a helical slinky that you can play with, it's a twisted, it can be represented as a twisted flux rope. And when this flux rope has enough magnetic pressure in it, it becomes unstable and it erupts out from the sun. Okay, so these two phenomena, which I will be talking about, are major sources of space weather impact. This figure is a real nice representation of what impact does, or what happens when we talk about space weather. So because these are really energetic events, they accelerate charged particles at the speed of light, and these charged particles can cause solar radiation storms. When the CME reaches the Earth, it can interact with the global magnetosphere of the Earth and cause geomagnetic storms. Any satellites that are in its path can be destroyed, or because it generates currents in those satellites, and that can disrupt their functionality. Also impacts the GPS, navigation, telecommunication, and mostly space-based technologies. Such events also can generate currents in the ionosphere, which leads to radio blackouts. So many such effects are governed by solar phenomena, and all of that is important for us to study. So let's see. Yeah. Recently, or in the recent times, we've seen how important and crucial it has become to study space weather, or predict space weather, I should say. That's actually a figure of, or the image of the power blackout that was sustained in Quebec in 1989 because of a large geomagnetic storm. This is more recent. This is the destruction of 40 Starlink satellites that were launched by SpaceX, and all of them were destroyed because there was a huge CME, which caused a geomagnetic storm, and it was billions of dollars of loss. These are the numbers that have been predicted, that if we don't improve our space weather prediction, or prediction of when a CME will reach the Earth, if it does reach the Earth, what will be its speed, what will be the magnetic field, how it will impact the global magnetosphere. If we are unable to do that accurately, there's a $100 billion loss to the space-based technologies. And of course, it impacts the power grids, it impacts astronauts, it impacts aircraft travel, etc. So hopefully I've convinced you that space weather prediction is really, really crucial, really important. And so then we'll talk about how can we do that. This has been an important topic in the heliospheric decadals for many, many decades now. And that's why there is a whole huge Helios fleet of instruments that are out there that study space-based or solar phenomena that impact space weather. That's the sun, that's the Earth, many, many satellites around us. What I will talk about are observations from these few that look at, that are both remote sensing and in-situ measurements of the solar outbursts or solar phenomena. This little thing is here to show you that multi-viewpoint observations are really important. So there's a satellite at Earth, which is, I think, SOHO. And then there's stereo observatories here, which go around in opposite directions to cover along the orbit of the Earth so that we can have multi-viewpoint observations. There are also many future satellites that are, in their preparation phase. We also know that the Parker Solar Probe and Solar Orbiter have reached closer to the sun. And then there are many CubeSats that are in orbit for these observations. And all of these are endangered because if there is a huge geomagnetic storm, which we cannot predict, all of them will be destroyed. Okay, so you can look at it in two ways. One is you want to observe everything in space. And the second way of doing it is to be able to model it here so that you can correlate what you're modeling with what is observed, and you can improve future predictions. So the way I have structured this essentially is I will talk about the numerical tools which are used to model these phenomena, then how the observations are used to inform these numerical tools. How do we quantify the uncertainty? How do we use data assimilation? And then what comes out? How well are we predicting it right now? All right, so I'll start with a modeling framework which has been developed for a really long time at the University of Michigan. It's called the Space Weather Modeling Framework, or SWMF, which is a combination of many models that represent different physical domains of space. So you start from the sun, you move out into the inner heliosphere, outer heliosphere. You model the global magnetosphere of the Earth. You can also model many different planets. There's also comet modeling. There's also exoplanets and astrospheres. But mostly what I'll talk about is sun to Earth domain. That's because that's what space weather impact really cares about. Okay, so this is a representation of what these models are. Now, let's see, I'll focus on the ones that are highlighted with green, but there's plenty models. So the way this is structured is you start from the sun. There's a numerical scheme to model or to solve the MHD, magnetohydrodynamic equations. From the sun, you move out into the inner heliosphere, and the information from the solar corona component of SWMF can be transferred in one direction to the inner heliosphere. So the arrow gives you the directionality of the coupling, essentially. Then once you model and this is used to model the solar wind, so in the three-dimensional domain. So once you have the solar wind, you can then add on top of it a coronal mass ejection, which is also parameterized. And I'll talk about it more, but this component is used, which is the eruptive event generator module that talks to the solar corona, and the solar corona talks to it. And then that flux-rope, or the CME, is put on top of the solar wind, and it erupts out and propagates out. And there's these observational inputs that also go into it. There are many other models that go into it, they're coupled to each other, they talk to each other. You can have particle tracking, there's particle in cell, there's polar winds, but other people do all of that. Okay, so why do we need a framework? Wikipedia describes framework as a universal reusable software environment that provides a particular functionality. Our space weather modeling framework consists of many such functionalities, essentially. There are different domains that are interconnected, but they can function as individual modules, but they can also couple with other modules and work as a whole framework as well. Each of these domains or each of these spatial regimes are described by mathematical and numerical representation. And the way that this framework is structured is that it also supports addition of other modules or other models and continuous development. This is just for knowledge that it's like just close to 1 million lines of code. In Fortran, C++, there's Python, scripts, there's Perl, there's IDL. And what a framework really needs is a huge set of files that can help you understand what the framework really is. So it's well documented, it's well tested. Every night we have a set of tests that run. So anything that was changed during the day is tested at night. And the next day, the person who made the change is blamed if something goes wrong. Okay. So, oops. All right. So let's now move on to how is the actual modeling done. What I'll talk about is the magnetohydrodynamic model that uses the solar corona and the inner heliosphere component of the space weather modeling framework, combines them into an alpha wave solar atmosphere model, or AWESOME, and it's used to model the solar wind and the coronal mass ejections. So I'll start with how solar wind modeling is done. But first, what is AWESOME? What AWESOME does is essentially, it's a first principle based model. So it starts from the lower transition region, extends into the corona and the inner heliosphere. It has outward propagating alpha waves and alpha waves that are reflected. So these types of alpha waves, which are forward propagating and reflected, they interact with each other. As a result of that nonlinear interaction, there's a turbulent cascade or dissipation, which heats the solar wind. And there's a magnetic pressure that accelerates the solar wind. And it solves MHD equations, but it includes also radiative cooling, heat conduction, and alpha wave turbulence, as I mentioned. Okay, so the heat that is generated is distributed over 3 temperatures. There's an isotropic electron temperature, and then there's perpendicular and parallel proton temperature. What comes out of this modeling, or if you do a simulation using AWESOME, what comes out is a 3-dimensional structure of the solar corona and the inner heliosphere. So when I say 3-dimensional, it means you can get at any point, you can get the density, temperature, magnetic field, speed, MHD variables, plasma parameters, everything at any location in space. Now, because this is a numerical model, it has a few input parameters. There are very few free parameters. And it is, of course, driven by observations. These are observations of the magnetic field of the photosphere of the sun. Okay, that's fine. So this is what a magnetic field observation map looks like. It's a 2-dimensional picture of the radial component of the magnetic field of the sun. So that is plugged into the AWESOME model. And what AWESOME model does is it uses this information at the inner boundary and has a few free parameters that are set. And there's a prescription to those parameters. And then it self-consistently models the solar wind solution, the plasma solution, everywhere in the 3-dimensional domain. Now, as I said, because you have information of all these parameters everywhere, you can extract those parameters at different heights or different wavelengths and synthesize outputs that can be compared to observations. For example, near the sun, you can synthesize extreme ultraviolet images from the model and compare it to the observations that are taken. You also have the 3-dimensional description or prescription of how the temperature looks like near the sun and further out. Okay, and finally, yeah.
Quick question. How do you measure the solar magnetic field?
Yeah. Well, there are many spacecraft that are doing it, but it's essentially Zeeman splitting. That's how they measure the radial components. Yeah. Yeah. So, and finally, this plot is what you will see a lot in this presentation from now on. So I'll spend a little bit of time on this. Observation in situ plasma measurements are shown here in black. So it's along the trajectory of the Earth. There are instruments that observe the speed, density, temperature, magnetic field, and components of magnetic field at the location of the Earth. And it can be integrated over a period of about 27 days, which is called a Carrington rotation. That's what is shown here. And because, again, our model is three-dimensional, we can extract from our model at the location of the Earth what comes out of the model output. That makes sense. Okay. And we can compare it to what the observations are. So you see, it's really cool. It can create, the model can actually predict this correlating interaction region that is seen in the observations. All right. Some other outputs that can be extracted from the model are flux of the energetic particles. There's also synthetic spectral lines and ion charge states that can be extracted from the model and compared to remote sensing observations. That's what other people work on. All right. So I said that this awesome model is driven by the observations of the magnetic field, right? But first of all, there are multiple spacecraft that are observing these magnetic fields. And they're slightly different from each other always in terms of how that data is collected or, what's the word? Calibrated. So we want to see how the input parameters or observed parameters impact these inputs or this model result. So there are two instruments that I'm showing here. One is the GONG, which is the global network of oscillatory network of something, and which is Earth-based, and it looks at the sun and looks at a small slit and takes measurements of the magnetic field and integrates it over a period of time. So for the same time period, that's what you get from GONG. Then there's another space-based observatory, which is a heliospheric magnetic field imager that is also looking at the sun in higher resolution, takes this output, or takes some output, and that output is put into a physics-based model called the ADAB model, which is a flux transport model that does some physics-based, adds some physics-based phenomena onto it, and produces another map. There's another way of using the same data where people at NSO are creating their own maps. And all these three maps, when put into AWESOME, produce three different results. So there's a lot of uncertainty which is associated with what is actually used to drive the model. And we want to quantify it. Okay. The next thing is the model has associated parameters. Now, how those parameters impact the output of the model is also important to understand. One of those parameters is the Poynting flux, which can be thought of as the amount of energy that you put into the solar corona, which will kind of dictate how fast your solar wind is, how much temperature or heat is generated in the solar wind. Different values of that parameter inform what output comes out of the model. That parameter is also dependent on the associated activity cycle of the sun. So during solar minimum and during solar maximum, when I say solar min max, it means how active the sun was during solar max and how the activity decreases during solar min. That optimal value of that Poynting flux also changes. So we need to understand both uncertainties associated with observed inputs as well as model inputs. Okay. So this was all about solar wind. Now, modeling the solar wind accurately is extremely important. And I'm at, okay, it's extremely important because that is what interacts with the CME when it is launched into the solar wind. And that informs how fast the CME will go, what will be the magnetic structure of the CME when it reaches the Earth. So accurately modeling solar wind is important. But then how do we model the flux-rope CME? Different ways of doing this. So different prescriptions of the flux-rope or the helical twisted magnetic structures are used. One of them is called the Gibson-Low structure, where it's like a stretched teardrop, which is what is shown here, and that's how it looks like in the model. And then there's also a toroidal field with a poloidal magnetic field component that can be used to describe the flux-rope. And the eruptive event generator within SWMF is used to do this. What happens is, or how it works is essentially you parameterize a flux rope, so which means that there are magnetic field strength, radius, and how fat the CME is. All those parameters are associated with a flux rope CME. And then you take that flux rope, put it on top of the solar wind solution that you have. Essentially, it means you add a perturbation at the inner boundary of the magnetic field and the density of the solar wind. And then that perturbation causes it to be unstable, and that flux rope essentially just erupts immediately. Okay, now this is also informed by observations of the magnetic field. So those magnetograms are used to decipher what is the size of the active region from where the CME erupts. And so based on that, what should be the strength of that active region? Okay. There's a really cool tool that exists and is open source to use to parameterize the flux rope. What the user can do is they can use the mouse to click on the positive and the negative portions of the active region where they want to insert a flux rope. And what that tool does is it finds what is the size of the flux rope, and the polarity size of the active region, polarity inversion line, and fits a flux rope on top of it, which then can be used into the AWESOME model, and it can erupt out. So I'm showing you just a general example of what comes out of AWESOME. This is a two-dimensional rendering of a time series of the CME output as it goes out. So if you look at the initial state, the speed is shown with the magnetic field lines. So all of these are magnetic field lines. And then you see a flux rope that goes out, expands out, interacts with the background magnetic field. Yeah, and then that's just at 2 hours what it looks like. So what else comes out of the model? Because this is, again, three-dimensional, global, you can extract whatever detail you want out of it. This is a Gibson-Low flux rope, and I will only talk about Gibson-Low flux rope at time t equal to 0. That's the surface of the sun. The flux rope is sitting on top of the background solar wind. 30 minutes later, that's the sun. The flux rope has expanded out, moves out. These are all magnetic field lines. The CME is propagating out. Now, CMEs, fast CMEs mostly, can compress the plasma in front of them and drive shocks. This is what a shock looks like in the model. So you can extract this compressed plasma regions, and you can kind of study the evolution of these shocks as well. And these are basically showing you how a flux rope that starts on the sun, how the magnetic field lines evolve and they open up as they move out. Okay. Again, because we want to bring out of the model things that can be compared to actual observations, we synthesize these outputs, which are similar to the white light Thomson scattered outputs from coronagraphs that are taken. What I'm trying to say is that there are instruments or coronagraphs that occult the surface of the sun and a part of the corona, and they take white lights, take images of the sun essentially, and they can capture how the CME is propagating out. And so at different locations, we have different instruments, and that's what we can extract out of the model also. This is another rendering of how the shock structure, the global shock structure looks like as it evolves out. And this is a time series of, again, the same flux rope evolving in time and the shock evolving in time. So it's great that we have all of this data, all of this output from the model. How do we know if it's correct? Well, we compare it with observations. The first one is, of course, the remote sensing observations, which comes from the white light coronagraphs. So you see here, the sun is in between somewhere here, and then there's an occultation disk. This is observation. And you see the CME structure here. And this is what comes out of the model. Both of these are from the same instrument, but different field of views. Then, because you want to do space weather prediction, you want to see what was the speed of the CME when it reached the Earth? What was it? What was the density? What was the magnetic field strength and the magnetic field components? Because those are the most important parameters. So we can compare those plasma parameters from the model with the results of or observations at 1 AU or at Earth. And we see that they match pretty well. Okay, so let me see. All right, so basically to this point, I want to say that this model is useful in modeling solar wind and compares well with the observations. You can predict the arrival of CMEs. You can predict when will it arrive, how strong it will be, what will be the impact at Earth. But when I started talking about all of this, I talked about uncertainty or input parameters that can lead to different results. So one of our projects was to study this uncertainty and quantify it. So it's a messy diagram, but I'll try to go through it. What we do is we take all the parameters of the model. We build a parameter space where we vary these parameters within a certain physical range. And then we do a large number of simulations. And we try to study, or we try to extract what is the contribution of each of these different parameters towards the output of the model. And then we associate a sort of an index or a sensitivity index to these parameters to determine, okay, this parameter has this much influence, another parameter has lesser influence. Once we do that, we can reduce the parameter space dimension, do another set of runs with a more optimal range of those parameters, compare with observations to restrict that optimal range much more, and then inform our future simulations so that we don't have to do those large number of ensemble simulations again for the future runs that we want to do for predictions. Once we have that, we have a set of background solar wind solutions. We then add on top of it the flux rope or the CMEs. Now, CMEs are also parameterized. So there are parameters associated with CMEs as well. So we repeat the same process. We build a parameter space, vary those parameters within certain physical range, do a large number of simulations, and learn from it using comparison with observations to determine what should be the optimal values for future prediction capabilities. Okay, so first, the solar wind ensemble simulations. We design a parameter space, and then we try to cover different phases of the solar cycle. Once we do that, we do about 200 simulations. To give a little bit of computational perspective, one simulation for the solar wind would take about 5 hours of actual physical time on 1,000 cores. So they are not cheap. Okay, so about 200 simulations each. Each of these lines is the output. result. And the black line is the model, observational output. Once we do that, we can kind of plot here the relative contribution of each of the model parameters, and how much of a contribution from these parameters comes towards the simulated output. And once we have that, we can restrict or optimize it more, compare it with observations, and then finally give a more reasonable optimal range of the model parameters and reduce the dimensionality, and then select some of those backgrounds into which CMEs can be propagated. And we do that again for each CME. We have a baseline estimate of the flux-rope parameters, vary those parameters, do about 300 runs for each of those CMEs, and then determine what is the most important parameter there that impacts the CME characteristics, limit that, and then inform future CME runs. This is a very, very small subset of the runs that we've done for 3 events. And what is shown here is, again, the plasma parameters. Black is the observation, and you can see how the different simulated outputs range based on how the parameters were changed. Okay, again, because you have many such simulations, you can compare it with observations that can inform, okay, this set of parameters of the flux rope were more important in the sense that they produced results that match the observation more. Okay, and because you have, again, 3-dimensional, you can do a time series comparison with the observation. Maybe in the interest of time, I won't do this, but I'll talk about in-situ comparison. So the end goal of all of this story is to be able to predict in advance when a CME will arrive. So if you see it happening on the sun, how fast can you model all of this and say, oh, in the next 20 hours, the CME is going to come here and the error is plus minus 5 hours. Right now, the community standard is 10 hours error, which is not really, it's, so plus minus 10 hours, which is not really enough time for any kind of safeguarding measures. So that's what we are doing. We are trying to improve that arrival time prediction. And from the first set of results that we have done, we've narrowed it down to plus minus 5 hours. So we can tell you when a CME is initiated or we see a flare happening. And we have observations of that active region. We can model that solar wind background based on how much we have learned from these solar wind simulations. We can narrow down that we don't have to do 200 simulations. We can do just 1 or 2 because we know what the optimal parameters would be. And then we model those, the solar wind. We add a flux rope CME onto it, let it erupt, and then it reaches the Earth, and that would be our prediction of the CME arrival. And so this is one of the results where the error time was just 4 hours. I think that's probably mostly what I wanted to talk about. So I hope the takeaways that I started with is where we have sort of landed together. In terms of what I've discussed is the numerical tool to model the sun to earth propagation of solar wind and the coronal mass ejections that impact CMEs, space weather. And I'm not an expert in stellar physics, but I feel like maybe all of those tools are also useful when you want to model stellar wind and stellar ejections. So what we have done or what we have achieved is also that multi-viewpoint observations are really important in informing how well your model is doing and is useful in kind of optimizing how to construct your model parameters so that you can get correct predictions. So So we have done this optimization. We have prediction of the arrival time error of about plus minus 5 hours. We've also accurately predicted the sign of BZ, which is the most important component for space weather, because that tells you how strong the geomagnetic storm is. All of this, and this is an important thing, is open source. So it's not, the model is complicated, but there are ways of someone outside the core group, I would say, for them to use the code, play with it, and analyze the results. And a lot of it is automated also, and it's all open source. And I think that's it. Thank you. Have any questions? Yes.
At the beginning, you said that there are 1 to 4 CMEs per day. How many of them are potentially important for Earth?
Oh, yeah, great question. Yes. So not all of them come towards the Earth, of course. During activity, when the magnetic activity is much stronger, there are CMEs in all directions. And I would say maybe 1 or 2 during a solar maximum phase come towards the Earth. And sometimes there are multiple CMEs coming out from the same active region that may be coming towards the Earth. What happens is, because it interacts with the background solar wind, sometimes the direction is changed. And of course, our magnetosphere is what protects us from it. So we don't see that much of an impact of it. But during solar maximum, I would say maybe 1 or 2 towards the Earth per day. Yeah.
I also say that those who are watching us online can just speak or write into the Zoom chat.
Okay.
Yeah, Maria.
Yeah.
Maybe you can tell us a bit more about the uncertainty analysis and the sensitivity analysis. Yeah.
Yeah, okay. So I'll try to do that. But we had amazing colleagues at the statistics department who did all of this analysis for us. But then essentially what it is they build a parameter space, a multidimensional parameter space of the parameters that we think that are free parameters in the model. And we, as modelers, gave them an estimate of the range that parameter can vary in. Okay. So then they build a parameter space where you have a different value of each of these parameters, and then you do these large number of simulations. Okay. Then what they did is then they collected all those simulated outputs, and they try to quantify, and it's called a polynomial chaos expansion, to using the global sensitivity analysis, or basically, in simple words, they associate an index with each of these parameters, and they say, okay, at this time, at the output of the simulation for the solar wind speed, one of these parameters had this much fractional contribution to the output. Then the other parameter at the same time for the output of the solar wind speed from the model had this fractional contribution. So you can kind of relatively see which parameter was more, had more contribution towards the variation of that solar wind output. And you can identify what are your quantities of interest. So for us, it was the speed of the solar wind and the density of the solar wind and the magnetic field of the solar wind. Those 3 are the most important parameters. And so they get the relative contribution from each of these parameters. Then they identify, okay, out of, let's say, 6 parameters, these 3 are the most important ones and have the maximum contribution towards the results. So what they did then was they limit the parameter space. So now we have, from 6, we have 3 parameters. We vary them, and because we could compare it with observations, we vary them now in an even smaller range. Do another set of less number of simulations and compare it with observations. So assimilate data into it to kind of understand, and you fit, I think they fit a Gaussian to the output or to the parameter space to determine, okay, this set of parameters for the 3 parameters will have more likelihood of producing the correct result. That's overall what they did. Yeah.
From the pictures, which one is the one?
This one.
Unaffected one?
Yes. And if you scan the QR, you'll find it there also. But yeah, the second one is full detail of what was done. Or you can, I'll let you know. Yeah. Any other questions? Yeah.
First of all, awesome, sounds awesome.
Yes, it is awesome.
I was computer guy. I was just curious about the computational complexity of running awesome, and if I think like if it spits out even like ±5 hours, how long does it actually take to run?
It's a great question, valid question. So to do a CME, when you already have a solar wind, it takes about 40 hours of physical time to do 4 days of computational evolution of the CME from the sun to the earth on about 1500 cores. It's not real time, but that's the point here. If you learn from this, you can do it faster than real time to do prediction. But there's also a component for awesome, which is called awesome R, which is a real-time awesome, that is computationally less expensive. So what it does is it does not model the near sun part, which is the most computationally expensive part, because it needs higher resolution, it's stretched grid, that's what's most expensive. So that awesome R is operational use, essentially. So what we learn from all of this is applied there, so that you can do it faster than real time. Yes.
About the parameter optimization, I imagine that from the graph side, to home that you optimize it from the path observation.
Absolutely.
But how consistent are they based on solar activity? Because then if you're optimizing the parameters, it's kind of biased to the path. If it is different in the future, then your model is kind of
it's skewed.
Yeah.
Correct, absolutely. You're right. So that's why we try to cover different phases of the solar cycle. Solar maximum, declining phase, solar minimum, and then accelerating up that phase towards where the magnetic activity is increasing. So I show very few results, but what we did was essentially try to cover the whole solar cycle so that we can kind of, so that it's not skewed, so that we can kind of understand what's going on during different phases. Yeah. Yes.
I have 2 questions.
Sure.
The first question is a bit question. So you said that you add perturbations. You add perturbations to the solar wind to produce CMEs.
Right.
I don't know. It's probably a nonlinear equation.
Yes.
So, given an input value, a small change in the input value will result in a small change in the output values. If it's not, then
it's not a small change.
So it is a chaotic system then.
How, I don't know. Do you define it as chaos? Maybe not necessarily.
I've seen a question just about chaotic system. At the distance of Earth, the error was ±5, but does this error increases exponentially, meaning that it is chaotic system, or it increases linearly in deterministic system? At distance of Mars, for example, compared to a distance to Earth, does the increase of is exponential or linear?
I would say it's ballistic. And the reason I would say that is, well, as you go, I mean, well, the data that we've used is only from the Earth. So there's already uncertainty as it goes out. So I won't be in a position to comment on what happens at Mars, but I would say that the way that this is structured is that the CME that is put on top of the solar wind solution, and it's like a perturbation to the inner boundary condition. So it's perturbations to the magnetic field and the density. And it's already unstable. So in reality, a CME actually builds. There's magnetic pressure that builds, there's a density structure that builds, and then slowly it initiates and goes out. That's not what's happening here. What's happening here is that you put a CME, it's already unstable, and then it just ballistically erupts. So there's no transition phase essentially to it. Goes out, so initially, as the CME is maybe up to 5 solar radii, it's still much, much faster than what's actually happening. So, but as it goes out, it slows down and then reaches the Earth at the right time. Yeah. You had another question. Yeah.
Okay. This is more kind of an exploratory question.
Okay.
So in the case of exoplanetary science, there are efforts put into observing auroras, especially in radio waves. Is it possible then to predict the magnetic field structure of the star based on the aurora observed in an exoplanet? I don't know. It's very exploratory, and so I think that will be like a moving in the opposite direction of what you are doing.
What you observe on a planet is what then can that inform what is happening on the sun. For the sun Earth system, it can somehow do that in terms of, okay, I do a simulation, I see that the CME arrives on time, and can I, based on the, and it is something that we do actually, in the sense that can we use in situ measurements or measurements at Earth to kind of connect what was happening on the sun. I have personally not done any of that, but I think the goal of the community is also to kind of connect observations at both the ends and try to inform one from the other. Yeah, I won't know the answer to your question.
Thanks.
Yeah.
Yeah.
About the predictions, are they actually used at the moment to protect some of the satellites, and what they are doing with the satellites to protect the CMEs?
Yeah. So so there's the Space Weather Prediction Center, which runs a lot of these models continuously every day, all the time. But those are computationally expensive. It's a form of awesome. It's not necessarily detailed awesome. And what they do is they give you predictions for every day, and they give you the index or like a measure of the geomagnetic storm or geomagnetic activity. SWIPC or Space Weather Prediction Center works with the national, it's called NOAA, so National Oceania Atmospheric something center in the US, where they are communicating with the government, where they do inform that, okay, there will be a CME, there was an observation, and in the next 20 hours, it's going to come to the Earth with an error time of whatever, plus minus 10 hours. So that information is given out. I don't know what they do with it. Yeah, we don't, I don't have, well, I'm an international scholar. I don't have any connection to any government organization there, but that is continuously done and it is communicated to people.
Actually, I was just a little bit embarrassed to ask a popular science question.
Oh.
Okay, let's assume that we know that a big storm is coming towards our satellite. What we can do about it? What I don't know. What any satellite company, or for example, if there is this Hubble Space Telescope, what can be done? Okay, we know it is coming, but what can we do about it? Nothing, just brace.
So well, brace, yes. I think one of the things that can be done in terms of just the operations of that satellite is to minimize those or like shut down the satellite if it's possible. Because if it's generating, if the solar panels are out and if there's electronic systems that are continuously working on it at that point of time, then the induced currents are what will impact that. because it's charged particles essentially. They will induce current in an already on electronic system and create havoc. We also know that space weather disturbances impact aircraft or aeroplanes, commercial and non-commercial. So if there is a timely prediction of such events, spacecraft travel, not just that, but aircraft travel, like commercial travel, can also be delayed, I suppose, so that it's less harmful because it's electromagnetic radiation. Then also it's astronaut safety. So if you can in time predict a huge storm, you can make adjustments to people on the International Space Station not going out and working on the thing. So these are important in the global scheme of things. Maybe I would say if there's a whole huge CME that's coming towards the Earth, there's literally nothing anybody can do. But thankfully, we have a nice global magnetosphere that will save us. So in terms of the space-based technology, I think what can be done is change the trajectory of the spacecraft a little bit. You can change flight paths a little bit. You can control how commercial aircrafts are flying, and all of that. In terms of all of that, this is useful. And the really cool thing in terms of popular science is you can track auroras. Yeah, that would be my answer.
I suppose having a contingency is actually much more important than people realize.
You're right, yeah.
But related to that, you had a piece of news in the beginning that 40 satellites were destroyed. Why those specifically? I mean, there are hundreds of satellites.
Oh, because
okay, they were not in orbit yet.
We didn't maintain their orbit.
Okay.
right, because there was a huge geomagnetic storm at that point of time that caused a large drag on those satellites, and those satellites started spinning and just couldn't regain their own life.
Because they were just launched and orbits and something like that.
Sorry, say that again.
Starting satellites, they start at very low orbit.
Okay, and then they are.
We have the big kind of CME impact, and kind of density of the atmosphere increases higher altitudes.
Right.
Okay.
Also, there's a lot more.
So events like that could be one potential, useful of it. Yeah. And it's millions of dollars of taxpayer money, so why not?
I have one more question.
Yes.
Is there a place where you feel like observations of sun are deficient somehow, or where would you improve the observations to improve the results from your models?
That's a great question. That's a crusade I'm on. What I want the community at this point of time is really rallying behind more multi-viewpoint observations of the magnetic field of the sun. The maps that I was showing you, those are empirical in the sense that there's a lot of empirical things that are done to fill those maps, because you don't see the poles all the time. You only see one of them and you don't even see it completely. So all of those regions of the sun are artificially, filled in when these maps are produced. And that leads to a lot of uncertainty in these modeling tools. That's one. So we want satellites and not just L1, but around, ideally, like a 360, a 2π thing that would continuously observe. Yeah.
I have also a popular science question.
Yeah.
Which is the best Aurora app would you recommend?
Oh my God. You know what? Twitter.
Okay.
Yeah, but there's a lot of, okay, seriously, there's the Space Weather Prediction Center, which gives you a map of the aurora every day. A predictive aurora every day. And that can kind of give you an idea of where you should go or as you are tracking it. Yeah.
Basically, look at space weather performance.
Yeah. Yeah, okay, thank you. Any other questions? Yes.
Are there any activities regarding using machine learning or artificial intelligence to kind of improve the models? So you have a lot of historical
Yes.
available. Then you have many parameters, and it's typical by, let's say, human brains.
Yes.
You have optimize everything. Right now, I think quite nice technologies to help.
Definitely, that's a great question. And yes, there are many groups that do space weather prediction that use machine learning and use past data. But they're doing it mostly for geomagnetic, like not the physical understanding of the physical phenomena. They're doing it for space weather prediction. So they identify the eruption on the sun, and then they, based on the phase of the solar cycle you are in, they can give you a prediction of when that CME will arrive. There's definitely that going on. There's also machine learning used to predict flares, the intensity of the flares that are erupting. So based on the morphology of the active region on the sun, they can predict how energetic the flare will be. So all of that is definitely going on in the field. And
it's dependent on the measurements you actually have. If you do not have proper observations when something happens, and machine learning machine tells you that something happens here, but what's actually going on, or what is what's happening, depending on specific parameters. And if you cannot observe the magnetic field of sun properly, then
yes, of course, that comes in terms of the limitations. But there's also, I would say, that the wealth of numerical modeling that the outputs that numerical models also produce can be used as like a, synthetic data that can be used for these machine learning models as well.